Hi everyone, in this video I'm working through the final part of question 14A of the 2020 Baulkham Hills Extension 1 trial exam. So this final part 4 follows on from part 1, 2 and 3, which I've already recorded videos for, so if you haven't seen them, take a look. I'll put some links into the video to make that easy to find. Part 4 says, by considering the dot product of vectors wy and wz, as well as the results from parts 2 and 3, show that wyxz is a square. So here we're at the final part where everything we've been doing before is leading us to this final result that we want to show, which is that these points w, y, x and z also form a square. So remembering the whole setup of this question is we had these two squares that were non-overlapping. We've now used vectors to be able to show that the midpoint or the center of those two squares plus the midpoint of the lines between them will also form a square. That's ultimately what we're showing. So yeah, let's take a look. So as I have with all the other videos, I've recreated the diagram just so things don't get too messy. I'll just annotate what we're being asked to show. So we want to show wy, so wy, x, z. So then if I link that back here, we want to show that's a square. Now obviously you can't just get a ruler and measure it and say, look, it's a square. First of all, I'm pretty sure my diagram's not to scale, it's not perfect. It kind of does look like a square, which I'm pretty happy with. But obviously with all these questions, we're not using measuring instruments, we're using, in this case, vectors or whatever technique is relevant. But in terms of this particular question, we're given a hint. We're told to consider the dot product of wy dot wz, making use of the dot product rule that theoretically, if you got through part 3, you'll know it, which means you can now apply it again in part 4. And I think it's worth also remembering, in the background to this question, we were told that wyxz is a parallelogram. And I think that's going to be useful to us now. So I've just noted it here so we don't forget. But if we start by thinking about this dot product, I think before we just throw in the dot product rule, actually I don't even think, we will need it, but I think to start with, a better place to start than just throwing out the dot product rule is to note from I think it was part 1 actually, where did we show this result? So part 2 we showed that these two are equal. Yeah, part 1 we showed wz is this and wy is this. Now the question said just use part 2 and 3, but I actually think using part 1 is a good idea too. So let's say, where are we? From part 1, we know that vector wz is f vector minus c vector. So vector wz is equal to f vector minus c vector, and wy is d vector minus a vector. wy is d vector minus a vector. Now, well, if we want to find wy dot wz, we can just throw these in and expand and see what we get. So therefore, we can say wy vector dot product wz vector will be equal to d vector minus a vector dot product f vector minus c vector. Now, in terms of dot product and expanding brackets, we kind of can just use our normal bracket expansion rules. So that's going to be d vector dot f vector. So d vector dot product f vector minus d vector dot product c vector. Maybe I'll just write those in alphabetical order. So minus c vector dot product d vector. So that's that and that. So now we'll have minus a vector dot product f vector, and then the minus minus will become a plus a vector dot product c vector. So that's expanding the brackets. Now, why that's potentially useful is if we go back to, let's see, what part was it? Part 3, we showed that a dot f, A vector dot product F vector is negative C vector dot product D vector. Now we've got a negative C dot product D vector, so I can insert A dot F in there because I know that's the same thing. So so I can say that's equal to D vector dot product F vector plus A vector dot product F vector minus A vector dot product F vector plus A vector dot product C vector, and that's from part 3. And the reason that's useful is because these can now cancel because it's a plus and a minus of the same thing. So we get left with D vector dot product F vector plus A vector dot product C vector. And now it's at this point that I think we can, well, I think it would be good to be able to use our vector dot product rule to kind of expand and see what we get, particularly because being squares, these angles between these vectors are going to be right angles, and if we just get our calculator out, cos of 90 is 0. So you kind of know things are going to disappear pretty nicely, but we've got to do the work first. But actually, we've got DFAC, but we know that the way the vectors have been defined, it was actually OA was 2A vector, OC was 2C vector, OD was 2D vector, and OF was 2F vector. So actually I'd like to have a 2D, 2F, 2A, 2C in there so that I can use my dot product rule. So if I want to do that, if I want to actually say let's put 2D vector dot 2F vector, to do that without changing anything, I've effectively multiplied this numerator by 4, so I'm going to have to then divide it by 4, so it's a quarter of that, and I can do a similar thing here, a quarter of 2A vector dot product 2C vector. And now I can use my vector product rule. So that's going to be a quarter times 2D vector dot product 2F vector would be the magnitude of 2D vector times the magnitude of 2F vector times the cosine of the angle between them. Now what's the angle between D and F vector? Well, it's a right angle because we're dealing with squares. So that's cosine of 90. And there is another bracket there, I think. And then similar thing here. We've got a quarter times, and all I'm doing here is I'm using the vector dot product rule that I outlined in part 3. So hopefully you're familiar with that. So that's going to be the magnitude of 2A vector times the magnitude of 2C vector times cosine again of 90. Another bracket. And as I hinted at with my calculator just then, I'll do it again, cos of 90 is equal to 0. So we're going to have a quarter times 0 plus a quarter times 0, because this 0 times these things is just going to cancel them both out, so that's 0. And therefore we can conclude, and I think there's probably enough room here, therefore we can conclude that the vector wy is perpendicular to the vector wz, since their dot product is 0. That is a result that hopefully you're familiar with. When the dot product of two vectors is 0, then that means they're perpendicular. So effectively what we're doing is we've got wy and wz, we're saying they're perpendicular to each other. And I think that's now looking pretty good, because remember, which part was it? I think it might have been all the way back in part 2. We showed that the magnitude of wy and the magnitude of wz are equal. So we showed that wy and wz are equal in length. We showed that in part 2. Now here in part 4 we've shown that they're perpendicular. So using what we know about parallelograms, which noting we have in WYXZ is a parallelogram, we can make use of that to get to it also being a square. So maybe I'll have to turn over at this point, but we'll say, how would we write this? I think since WYXZ is a parallelogram, we can say that what do we call it? I think the way we say it is the consecutive angles of a parallelogram are complementary. So we could say angle ZWY plus angle WYX plus angle WYX is equal to 180 degrees. So consecutive angles of a parallelogram are complementary. I've just used a lot of shorthand there, but hopefully that makes sense to you. That's how I kind of learned to write things in shorthand mathematically. If you didn't learn that, or if you don't think whoever's marking you would understand that, just write the words out in full. But since we just showed that ZWY is 90, we can say 90 degrees plus angle WYX equals 180 degrees. Therefore, angle WYX equals 90 degrees. Or in other words, this is also a right angle. Now, maybe at this point, you could repeat this over and over again, or you could say something like similarly, and just, you know, instead of writing your reason out every time, you could just write WYX angle WYX plus angle YXZ equals 180. So therefore, angle YXZ would be 90 because we've just shown WYX is 90 and we subtracted over. And finally, so I'll just annotate on our square, our 90 degrees there. Now, finally, angle YXZ and angle YXZ plus, so YXZ plus XZW, angle XZW is equal to 180. Therefore, angle XZW equals 90 degrees, since that we showed was 90, so 180 minus 90. So we can annotate on our last angle. So we've got all interior angles are 90 degrees. Now, the other thing we can note about parallelograms is that their opposite sides are equal. So we can say, we could again say, since WYXZ is a parallelogram, we could say WZ is equal to YX. So the magnitude of WZ equals the magnitude of YX, since opposite sides of a parallelogram are equal. So you probably learned that quite a few years ago, but here in Extension 1 we're being, again, as I mentioned in an earlier video, math follows a spiral curriculum in New South Wales, so you're constantly deepening your knowledge of what you've learned in earlier years. So it really shows the importance of, you can't really just like cruise through math in year 7, 8, 9, 10 and 11 and then say in year 12 I'm gonna really start focusing, because actually you've then got 5 years to try and catch up on. The better approach is to consistently work hard at your math over all the years, because it's all leading to this final HSC. The spiral curriculum means if you want to make your life a lot easier, spread the effort over the 5 years and constantly deepen your knowledge. Anyway, that's a little side point, but so we're relying on opposite sides of a parallelogram being equal, so therefore we can say WZ equals YX, or in other words, this equals this. And similarly, WY equals ZX. The magnitude of WY equals the magnitude of ZX. Magnitude of WY equals magnitude of ZX. So that kind of gives us what we need. So we can say, therefore, WYXZ is a square since all sides are equal and all interior angles are 90 degrees. And I reckon that's enough to convince a marker that you understand why WYXZ is a square.
Panic boom!
Alright, there you have it for that question. I think it really did require us to put together a lot of our knowledge. I've used a result from part 1. I used the result from part 2 about these two sides being equal. And we also used our result from part 3 to help simplify this dot product. So yeah, all 3 parts were leading us to this final question where we could prove this result. It's an interesting result if you think about it in general. We got 2 squares that were non-overlapping. We picked their centers and we picked the midpoint of the lines between them, and that itself gave us a square. I think if you were to investigate that, take the time to really investigate that, hopefully you'd find that to be pretty interesting. Yeah, so there you have it on that question. Hopefully all of that made sense and you found that helpful. And yeah, tick boom.